part, we're going to use the isotope satellite lines to essentially count the number of atoms of a particular type that are in a polyatomic molecule. In this introductory course, we're only going to look at polyatomic molecules containing the elements carbon, hydrogen, nitrogen, and oxygen. The mass spectra of each of these elements was discussed in part 1 of this lecture, and we came up with the following pieces of information regarding the characteristics of each of these 4 elements. So carbon, two isotopes of interest, carbon 12, carbon 13. Carbon 13 has a 1.1% abundance. Nitrogen has 2 isotopes of interest, nitrogen 14 and nitrogen 15. Nitrogen 15 is present in 0.4% abundance. Oxygen likewise has 2 isotopes of interest, 16 and 18. The oxygen 18 is present in an abundance of 0.2%. Hydrogen has only 1 isotope of interest. The other 2 that you know of from general chemistry are in such low abundance that they're not detected in most analytical mass spectrometers. So we're going to use the abundance of the isotope lines, namely the A+1 and A+2 isotope lines, to in effect count the number of elements of each type in the molecule. Let's start with a simple molecule. Just think of methane. It's been ionized so that the parent molecule, namely the full molecule, comes through the mass spectrometer analyzer intact, missing just 1 electron. So it's going to have a M to Z of 16, and you'll see the A+1 satellite line for the carbon at 17. If we look at carbon monoxide ionized, and if this to come through unscathed, unbroken through the analyzer, we would see as the parent ion, charge of +1, appear at M to Z, mass to charge ratio of 28, with the carbon isotope line at 20, giving us a peak at 29, and the oxygen isotope line at 30. So we would see the following pattern. Now, to analyze this and actually do the counting, you essentially make yourself insane looking at the histograms. So the histograms are of limited use, so we will also be presenting with mass spec data tables of the actual abundances as measured by the analyzers. So in a modern mass spec, you would get both pieces of information. And we could see the 100, the instrument has auto-scaled, set the dominant line to 100% abundance. The A+1 line is 1.1% relative to the line at 28. And the feature at 30 is 0.2 relative to the large peak at 28. So let's look at building up a carbon skeleton and begin with C2 and just pretend that this is a molecule with +1 charge. We would expect to see major peak at 24, another peak with the A+1 at 25, and who knows what happens at 26. If we look at the probabilities of the different isotopes, we know that we have a probability of seeing a carbon 12 of 0.989. We see a probability of a carbon 13 for a single carbon atom, 0.011. So if we start making the diatomic molecule, so carbon 12, the probability of having 2 carbon 12s on that molecule is the square of 0.989, namely 0.987. If we look at the combination of 1 carbon 12 and 1 carbon 13, we have 2 times the probability of seeing the carbon 12 times the probability of seeing a carbon 13, namely 0.011 times 0.989. The reason there is a 2 there is because there are 2 ways to make that molecule. I'm pretending I can actually identify the different carbons in the molecule. Okay. And finally, if we want to know the probability of seeing a diatomic carbon-13 molecule, we multiply 0.011 times 0.011 to get 0.00012, so a very low probability. So I would expect in my abundance table to see this. Maximum peak having an M to Z of 24. The M to Z peak at the M to Z 25 peak has an abundance of 2.2, as indicated in my little probability experiment there. And the 26 is, forget it, I'm not going to see it. It's just not going to happen. It's below the detection level of most analytical spectrometers. So this suggests to me that I might be able to do some counting, right? I've got 2 carbons, and I seem to have doubled the abundance at the A+1 position. And that's actually what we're going to do. So the premise is that for carbon, if I look at the A+1 peak, the number of carbon atoms in the skeleton of the molecule will give me an A+1 peak of n times 1.1. I want to prove that because this could be completely bogus or a coincidence from the last slide. So let's take an arbitrary carbon skeleton Cn. The A peak is going to have a probability, namely n times 12, carbon 12s, of 0.989 to the nth power. The A+1 peak, 1 carbon 13 and n minus 1 carbon 12s, would be n times 0.011 times 0.989 to the n minus 1 power. The relative abundance of the A+1 to A is going to be the ratio of those probabilities, which gives me n times 0.011 times the 0.989 to the negative 1 power. So this is going to be giving me roughly 1, or a little bit more than 1. So in fact, my A+1 is going to be indicative of how many carbons I have. So the upshot of this is if I have a carbon-based molecule, polyatomic number of carbons in the skeleton, if I divide the A+1 peak abundance by 1.1, I can get an estimate of the number of carbons in the molecule. And I could repeat this process and analysis for the A+2s of oxygen and the A+1 of nitrogen as well. So I can use the A+1s, A+2s, divide by the isotopic abundance of the individual element, and essentially count by division. You were probably expecting this, but the boss says not so fast. You've left out a key ingredient or a key factor in determining the reliability of that hypothesis. So all instrumentation methods have an associated error. In the typical analytical mass spectrometer, there's a measurement error in the abundance, and there is a rule of thumb which is applied to estimating the error in your table of abundances. So you take 10% or 0.2 absolute, whichever one of those numbers turns out to be larger. So if we look at the C2 data, we have at the M to Z 25 peak an abundance of 2.2. If I apply the 10% rule, I get 0.2 plus or minus 0.2 as the abundance. So, and I would get the same if I applied the absolute in this particular case. If I applied the 10% to the 26 peak, that comes out to a meaningless number. So in this case, if I were to want to apply the error to the 26 peak, I would apply the 0.2, and I'll do that in the next slide. So if I look at the carbon-oxygen mass spectrum, I got this table of data. So the parent ion goes through as MZ28. It has isotopic satellites at 29 and 30, which were visible. If I apply the 0.2 absolute rule, since 10% gives me a smaller value in both cases, I have plus or minus 0.2 for the 29. I have plus or minus 0.2 for the 30, and this points out a conundrum, well, something, a problematic aspect of dealing with mass spec. The error in the case of the A+2 when oxygen is around is as big as the oxygen. So there's a good chance that in a given mass spectrum, I'm going to be a little bit off in my estimates on the oxygen. So I have to be careful, and we'll deal with the way to get around this problem in part 3 of this lecture. We're going to develop truth tables, in other words, to make things a little easier for ourselves. And finally, here's a more extreme, a larger molecule, a more significant real molecule that will really point out the issues when it comes to interpretation. So if I have benzene, I have the expected peak at 78. I get the expected peak at 79 for the A+1 carbon. I've got nothing at A+2, but as I'm about to show you, that doesn't really mean anything. You have to be kind of careful. So initially I would say there's nothing at A+2, no oxygen. However, when I look at the table and I start applying the errors, I start to get a little worried because I have the following as indicated. I have an error of 0.7 on the A+1 peak. Even though I have 0 at the abundance, I have to apply the minimum rule, or the maximum rule rather, on the error, and I apply the absolute 0.2 at the A+2 peak. So that gives me a range, in other words. So for the A+1, I have a range of 5.9 to 7.3 in the abundance. And 7.3, if that were to say at 7 carbons, that's too big. It's going to give me more than 78 atomic mass units. So I don't want to go to 7, but 5.9 is just outside the range of 5 carbons. So do I have 5 carbons or do I have 6 carbons? Similarly, if I look at the A+2 error, I have a potential range of 0 to 0.2. So do I have 0 oxygens or do I have 1 oxygen? Clearly, if I had 5 carbons, I could combine that with 1 oxygen and possibly get a reasonable molecule. I can't have 1 oxygen with 6 carbons and still have an N to Z with an AMU, in other words, a molecule with AMU under 78, or at 78. So there's going to be a little bit of guesswork in the interpretation of mass spec. It's not, it's not a concrete result, but well, as we're going to find in part 3, we're going to come up with techniques to limit the number of guesses and make educated guesses in the interpretation. So clearly the cat was right, and we're going to have to do some other thinking when we interpret mass spec. So this concludes part 2. The bibliography regarding the interpretation and the application of the adding rules that I've just applied can be found in any introductory textbook on interpreting mass spectra. These two happen to be very good.